Hey, Alex and Randall. You have any questions? Feel free to ask them. We got about 8 minutes before class starts. Guess I should probably check, make sure my share screen function works again. Looks like it is. Yes. Okay. That's all seems to be working well. Feel free to ask me any questions if you have any there, James. We still got about 6 minutes left.
Professor.
Yes.
I just wanted to remind you, I still have that 2 weeks in April that will be gone.
No problem. Appreciate that. Remind me when you get there as well, because I'll forget again. In fact, I had a student last night. Like, got mad at her and like browbeated her, like, I can't believe you missed the final, but I mean the midterm, and it was a student I'd already talked to about having to miss because she was going out of town. So I sent back an email, said, I'm sorry, it seemed like I was browbeating you. But yeah, just remind me again, and then I'll probably forget when you get back anyways. But just bear with me if I accidentally browbeat you when you get back.
I mean, when I do get back, it's gonna be after the school semester.
Oh, that one. That's right. Okay, yeah, I remember your issue now. That was the deal where you're going to be away, but you can still get stuff done online, right?
I don't think I'll be able to do it online.
Okay. All right. So that, yeah, maybe I was thinking of some other student then. This is James, right?
Sir,
Okay. So yeah, what we normally with that kind of scenario, we put up an incomplete and then you just complete it when you get back. And I can give you like a, probably a 1 or 2 month window to get it done. And I'll work with you. We can get it done in the summer or something like that. It won't be a big deal.
Yeah, that'll be good.
No problem. We've still got about 4 more minutes. Feel free. Anybody else ask me questions?
For the test corrections for the
Mhm.
midterm, will will you have like written directions on that?
Yes, I'm actually writing the directions right now as I speak. I'm
All
actually
right.
putting it in a window at this time, and it'll be your class is getting it first. Another one coming in. All right.
Excuse me, one question real quick.
Uh-huh.
With the midterm, you said that we could make up the problems that we got wrong, or do we have to go through the entire test?
All of it. The whole thing.
All, okay.
Yep.
Thank you.
You're welcome.
Professor, I just wanted to make sure I heard that correctly. You want us to go over all of the questions, even the ones that we got right, or?
Yeah, absolutely. I want you to do the whole thing over again. Work every problem. What I'm writing down right now, I said the format should be number one, and then write the exact wording of problem number one with the available multiple choice options. Then write solution, neatly write your solution, and even explain steps with full sentences if you have anything even remotely complicated. And then do number two, solution, so on and so forth. Complete the entire exam. And all of that should be saved as a PDF. So you can either take photographs of it and put it in a Word document, save it as a PDF, or I use a device that actually allows me to take photographs and it turns the photographs directly into PDFs. Whatever you want to do is fine. It just has to be turned in as a PDF.
May I ask, is there any way to turn off lockdown browser when viewing our results for the exam? Just because it would be really hard and a lot of extra work to write down every single question if lockdown browser was taken off, then I could just copy and paste each of the questions.
Yeah,
Do you
is
see
it
what I'm
letting you
saying?
do screenshots? I was thinking you could do a screenshot and then copy.
Like a screenshot and just like enter the question into like the Word document, just do it that way.
Yeah, that's what
Okay.
I pictured you guys doing.
Okay, all right, that makes more sense. Okay,
Yes.
thank you.
Yeah, see if that works. Command Shift 3 if you're on an Apple computer. There's a nice little app if you're on a Windows computer, just called Snippet or something like that.
Okay, thank you.
And you want us to just email this to you?
No, I'm putting up a link right now in this week's module, and it's
Okay.
going to be under extra credit.
And when's this due by?
A week from today.
Okay. All right. Awesome. Thank you.
No problem. You're welcome. Okay, I just finished writing that up. I'm putting the due date as the 29th. And I'm actually making it the 29th at 11:59 p.m. So you actually have that whole day as well if you need any last minute stuff. All right, it's 5:23, so that means we're actually past the classroom time. I have now completed, it's just called midterm redo, and it's listed as I think I called it an imported assignment, so it doesn't actually affect your grade, but that means I'm just going to grade it and then put it into the grade book on your actual midterm score and put a note on it so you and I can both tell what happened. So that looks like that's going to work. Anybody else have any questions before we get started? We're finishing up chapter 9 tonight, jumping into chapter 10 next time.
How's your day going?
Pretty good so far. I actually got to cover quite a bit of material in my 241 and my 242 class today. The lab went to crap, but oh well. That's why I'm a theoretical physicist instead of an experimental physicist. I can't stand being at the beck and call of a piece of machinery that's just dumb. And today we had like virtually every problem that could go wrong mechanically did go wrong. So mechanically and or electronically. But other than that, it went well. Thank you for asking. So last time we had worked out collision problems, and specifically, you might not realize it, but if you look in the e-text, you'll see that the problem I derived, that first one I worked, I think it was the first one I worked for one dimension head-on collision. I actually worked problem 34 from the end of the chapter 9. Because that's basically a case where MA, so you had a particle of mass MA moving with velocity VA, runs into a particle of mass MB that happens to have a velocity VB. And then after the collision, which is head on, by the way, so that they both all stay in one dimension. After the collision, MA has a velocity of VA prime and MB has a velocity of VB prime. And I actually worked out in detail what is a VA prime and what is VB prime. And in fact, I finished it at the end of class, even after you guys left and finished writing it out. So I've actually done quite a bit of work there. I explained what I was doing while class was going on, but that remaining part, I didn't do much explanation. That was just a matter of working with algebra. So by all means, take the time to look at the video and remember also this thing when I'm writing this stuff in, I named the file for this with the exact same name that I use for the actual video on my YouTube channel. So for instance, today's video is called PHY. Well, I say it's called, this is actually the file. So the video will have an entirely different name on my YouTube channel, but you can still do a search for this part. So I'm sitting, getting ready to put it in chat. but basically it's PHY 241 N01B underscore 03222023. So that's the name of the file that I upload to my YouTube channel. And I immediately pull that out of the title and just leave it down in the notes. And then I write a regular title. But I take this document that I write my notes in as a PDF. That's uploaded to my Google Docs page, which you all have access to from either the first or second module in Canvas. And you can find today's notes with that exact same name. Okay, so it should help you. Not only that, if you're looking for other ones, you can find them by the same method. And in fact, you can look at all my 241 notes just by typing in PHY 241, and then you'll see all the dates and all that stuff come up. So any questions on that? Everybody understand what I'm doing there? Okay, so all I'm saying is you have access to these. Sometimes I actually take the time to post a link to the video in Canvas. The other times I just post it to my YouTube channel. And I do recommend and ask that you subscribe to my YouTube channel, just because you'll actually get an email notification every time I post something new up there, so you can actually find it. Feel free to unsubscribe when you're done or whatever, when the class is over or whatever. That's fine too. I'm just getting it so you guys can find it. So as a continuance of last time, we now have to consider the problems of a two-dimensional collision. So in other words, a collision in which the initial particle is moving with some velocity parallel, say, to the x-axis, and the other particle is sitting perfectly still, and then they collide and move off with angles with respect to the x-axis. Okay, now that might not seem as general as possible, because it seems like a more general problem would be one where the other mass mb is also moving. Well, it turns out that it's as general as it needs to be, because you can always switch to another reference frame. So for instance, if particle B is moving at 60 miles per hour to the left and particle A is moving at 60 miles per hour to the right, we can move to the rest frame of particle B by moving 60 miles per hour to the left. So in other words, we're going to make each velocity, for instance, the velocity of A will be VA minus 60 miles per hour, or excuse me, VA plus 60 miles per hour. Sorry about that. And that's a conversion from the velocity that it had in the at-rest frame to the velocity that it has in the B frame. So when I do that, when I actually add 60 miles per hour to all the velocities, then I'm getting the velocity in that new frame. So for instance, the velocity of the particle B, which was negative 60 miles per hour, is now going to be negative 60 miles per hour plus 60 miles per hour, which gets you 0. And to compensate for that, we're also adding positive 60 miles per hour to velocity A. So that gives you 120 miles per hour. And then when you get done, you solve it all, you got theta and all that stuff. You just have to convert back by adding, instead of plus 60 miles per hour, now you're going to add a negative 60 miles per hour, and that'll bring you back to the true at rest frame, or true as it can be. So anyways, that's why we don't need to go any more general than just a particle with two particles colliding, only one of which is moving, and the one that's moving is moving parallel to the x-axis. Because the x-axis part can be seen, because you can basically make the x-axis any direction you want. So even if the particle is moving up in this way, you say, okay, well, I'm going to define the x-axis to point that way. Okay. All right. So with that in mind, let's start off with an actual problem. And this problem is going to be basically two pool balls, billiard balls, moving. Velocity A is going to be at 3 meters per second, And since they're billiard balls, both of them have the same mass. So MA is going to equal MB, but MA is going to equal MB. So why don't we just call it M? So that's what we're going to do. And then after the collision, what we discover, or what we're told, is that the theta A prime is in fact going to be 45 degrees, and theta B prime is going to be downward 45 degrees. So that'd be negative 45 degrees. So I'll write this information down here, and I'm going to go ahead and share a screen. So let's share screen. Okay, so what I have is M sub A is equal to M sub B is equal to just plain M. What I have also is V sub A is equal to 3.0. I'm going to go 2 sig figs meters per second. And theta A prime is equal to 45.0 degrees, and theta B prime is equal to negative 45 degrees. And that's because I measure it clockwise from the positive x-axis. So I'm going to draw a drawing of that really quickly. Let's say there's my x-axis. There's my y-axis. And what I'm imagining here is particle MB right there. And what I have here is particle A moving with velocity VA. Then after the collision, what I find is this is particle A, this is velocity VA prime, and this angle right here is theta A prime. Similarly, this is VB prime. This angle right here, actually, technically I should call that negative theta B prime, just because I measured it. I'm showing the actual arrow. Actually, it'd probably be better just for me not to show the arrow, then that way I can just call this theta theta B prime. Okay. So that's what's happening here. I've actually gotten the angles. Obviously, I did not draw this drawing to scale with respect to the problem, but that's just a generic solution or a generic drawing for all solutions. Now I'm going to go ahead and solve it. What I want to know, of course, is VA prime is equal to question mark, and VB prime is equal to question mark. Okay. So my solution. So these are particles in principle, or actually these are pool balls in principle. And as pool balls, unless you really drastically put some spin on it, and actually I shouldn't say drastically, if you put spin on it, all bets are off with regards to forces acting on it. But if you just sort of hit it sort of flatly and it rolls without slipping, then basically the net force acting on it is 0. And if you treat the system to include both balls, then all the forces are 0 because collisions are internal forces at that point. So that means momentum is conserved, because that's the necessary condition, is that for momentum to be conserved, the net force acting on the system must be 0. So I'm going to conserve momentum for starters in the x direction like this. I'm going to say that the mass, which remember we said MA equals MB equals just plain M. So I just wrote M times VA is equal to M times VA prime times cosine theta A prime plus M times VB prime times cosine theta B prime. So hopefully you can see that that of course is what you expect to get for the x component, because cosine is going to be the, of course, giving you the adjacent component of the velocity or momentum in this case. So that's one of them. And now you can see immediately that the masses cancel out. In other words, I can divide both sides by m, and of course I just get VA is equal to VA prime cosine theta A prime plus VB prime cosine theta B prime. So I'll go ahead and write that again. I'm just going to say VA, I'm going to say VA is equal to VA prime cosine theta A prime plus VB prime cosine theta B prime. And that's going to be equation 1. Now I have equation for momentum in the y direction. So in the y direction, notice VA is moving parallel to the x-axis, or I should say mass A is moving parallel to the x-axis. So VA has no y component. So literally the left-hand side is just going to be 0. The right-hand side is going to be VA prime sine theta A prime plus VB prime sine theta B prime. And that's going to be equation 2. Notice I've already canceled out the mass. Technically, I should have left that, but I wrote it before I thought about it. So I'll just say so you see that the left-hand side would just be 0. The right-hand side would have a M between the equals and the VA prime and a M between the plus and the VB prime. Therefore, I could divide both sides by M and I'd have no M's left. And that's how we got 2. Does everybody, does that make sense to everyone? All right. Seems like it does. So what I'm going to do now is I'm going to go ahead and plug in my values and try to solve for this equation 2. So from equation 2, I'm going to say that VA prime times the sine of 45.0 degrees plus VB prime. Oops, I forgot VA. Might help if I put the VA over there. Oh, actually it was 0. That's what I'd forgotten. Okay. 0 is equal to VA prime sine 45.0 degrees plus VB prime sine negative 45.0 degrees. Now, if you look at your graph of sine, which I'll put right here just as a reminder, your graph of sine looks like this. Okay, and of course it continues on this side like this. So you see that the sine of negative theta is equal to the negative of the sine of theta. That's because sine is an odd function. Okay, cosine, on the other hand, is an even function. So using that identity, what I can do is now say, let's pull VA to the left-hand side, and I'll get negative VA, actually I should say VA prime to the left-hand side, and I get negative VA sine 45.0 degrees is equal to, now, since I'm taking the sine of a negative angle, I can just replace that with the negative of the sine of the positive angle. So I'm just going to put negative VB prime times the sine of 45.0 degrees. And now you can see that the negatives actually cancel out. And I think you can also see that sine of 45 is going to cancel out as well. So hopefully this was already obvious from the symmetry of it, but if it's not, it should be now. VA prime is equal to VB prime. So we now know that that's one part of the problem. So once I figure, or one part of the problem solved. So once I figure out what VA prime is or what VB prime is, I automatically know the other. So I call that equation 3. And the reason why I said that should be obvious is, notice if mass A went up at 45 degrees, whereas mass B left at negative 45 degrees, they both did more or less the same thing. And because they did the same thing, that means they are acting sort of on an equal footing, and the symmetry of the situation would suggest that the thing going to the positive 45 degrees should have the exact same numbers as the thing that went to the negative 45 degrees, or you would have had one be like 30 degrees and the other one be like 60 or something like that, or maybe 30 and 25. The main thing is you wouldn't have the same angles from the symmetry. So that's why I said from the symmetry of it, you'd sort of expect that. What you may or may not have necessarily expected was that the two angles should ultimately result in the two velocities leaving at 90 degrees from respect to each with respect to each other, and that's exactly what's happened here. But they gave it to us in that way. It turns out, I haven't shown it here, but it turns out that in fact that's always going to be the case when the masses are equal. If the masses are equal, you're automatically going to get that the two velocities after the collision will add to give you 90 degrees. Okay. All right. Now I'm going to plug 3 into 1. And in doing so, this is what I get. I get VA is equal to 2VA cosine 45.0 degrees. Now, here's what I did. I used another fact again for this one. Specifically, if you look at the cosine graph, the cosine graph looks like this, and the negative values look like that. You can see that the cosine of negative theta is actually equal to the cosine of theta. So that's what I did, is I replaced the cosine of negative 45 degrees with the cosine of 45 degrees, so that now those two terms are actually like terms, and I left off a prime there. Now I've got the prime. Okay. So that's what happened when I replaced VB prime with VA. So now I can see that VA prime is actually going to be equal to, automatically we know it's going to be equal to VB prime, because that's what we found in equation 3, but it's also going to be equal to VA divided by 2 times the cosine of 45.0 degrees. You probably remember the cosine of 45 degrees is root 2 over 2. So basically, VA prime equals VB prime is equal to 3.00 meters per second divided by 2 times the square root of 2 over 2, which equals just 2 divided by the square root of 3 divided by the square root of 2, which I think is 2.12. I will check that real quickly. So 3 divided by parentheses 2 times, here's where I'm testing cosine 45, close parentheses. And that gives me 2.121, carrying 1 extra sig fig. So that's it. Doing 3 sig figs, I got 2.12 as my answer. Any questions on that? So the physical principle we learned here is basically, hey, if you, especially if you have a elastic collision, in fact, this one turns out to be essentially an elastic collision, if I'm not mistaken. But if you have an elastic collision, then you automatically would have 1/2 mVA squared is equal to 1/2 mv a prime squared plus 1/2 mvb prime squared. Well, if you divide through by the 1/2 m's, you're going to just get VA squared is equal to VA prime squared plus VB prime squared, which is the Pythagorean theorem. So that's why I'm telling you this 90-degree angle that popped up, which is a ramification of collision where you have equal masses, that automatically has made it look like it's also a conservative elastic collision that conserves kinetic energy. So, any questions on that? All right, somebody is trying to come in again. So now what I'm going to do is I'm going to solve another problem again, using a two-dimensional conservation of energy situation, or excuse me, conservation of momentum situation. But in this case, it's actually a proton traveling at a speed of let's say 4.0 times 10 to the 5th meters per second. And it's going to collide elastically with a stationary photon and a hydrogen target. And one of the protons is observed to be scattered at an angle of 60 degrees. At what angle will the other proton be observed, and what will the velocities of the two protons be after the collisions? So that's actually 3 variables we're looking for. Luckily, they gave us the fact that it's elastic collision. So that means that we got 3 equations to use. So yay, we can do it. So let's see, we're going to say this is going to be a proton. Well, I think I'm going to write it proton for some reason. Okay. This velocity VA is going to be 4.0 times 10 to the 5th meters per second. And it's going to, in fact, run into another proton, which has VB equal to 0. Now, after the collision, we're going to have, let's draw my axis real quick. So I'll draw an axis like this. And I'll draw an axis like this. And this will be my x-axis, and this will be my y-axis. And now I'll go back to red. No, I can go to blue this time. And what I'm going to do is say that this guy is, and it's really arbitrary which one you consider this to be. I'm going to pretend like this one is the proton A. So this would be particle A, and this would be VA prime. And this angle right here, theta A prime, is equal to 60 degrees. And actually, let me go ahead and use 3 sig figs. And I'm going to say it's 60.0 degrees. And I'm going to call this speed over here 4.0 meters per second, which allows me to do this stuff. I gotta make this a little neater, or it's gonna drive me crazy. Well, that's just stupid. Okay. So now I've got that situation, and also this other particle is going to come out at some other angle. And in fact, the other particle is also a proton, but this one's going to have an angle theta b prime equals question mark. VA prime is equal to question mark, and VB prime is equal to question mark. Okay. So I've now written down all the information. I know it is an elastic collision. And elastic means kinetic energy is conserved. Okay. So now I'm going to write down my equations. Let's say I want to work the solution in black this time. So first off, I have conservation of the x momentum. Conservation of the x momentum says that m times VA, which we know, is equal to m VA prime cosine theta A prime, which we know. Again, we can't technically tell one proton from another. I'm going on the assumption that we're going to pretend this is particle A, and then from that I can figure out what the velocity of particle B is and the angle for particle B. If I find out I was wrong, then I just have to rework it again, calling that B, but in fact, I'd get exactly the same result, so it doesn't really matter. Plus the other one, which would be M times VB prime times cosine theta B prime. Again, since the masses are all equal, we can just divide those out, and I get, in fact, equation 1 is VA is equal to VA prime cosine theta A prime plus VB prime cosine theta B prime. Now, I would be inclined to go ahead and do some work with this right now, but I think that's a little misleading because I know what's going to happen with this. That's why I want to do that work, but I'm going to skip and I'll come back and alter this equation a little bit later. So now I'm going to conserve momentum in the y direction. And like I told you, we've been treating it as if the initial velocity of the one that's moving is along the x-axis, and that's perfectly general because we're always allowed to make our coordinates point in any direction we want. So in this case, it's not going to have any component of momentum in the vertical direction. So I'm going to write 0 is equal to, technically we would have the mass. Last time I just left it off because I knew I was going to divide it out. I'm trying not to do that this time. So in this case, it's going to be MVA prime sine theta A prime plus MVB prime sine theta B prime. That's going to be, well, let's go ahead and divide through by the mass. That'll give me 0 is equal to, that's going to give me 0 is equal to VA prime sine theta A prime plus VB prime sine theta B prime. That's going to be equation 2. And now I'm going to conserve kinetic energy. So remember, kinetic energy is 1/2 mv squared. When we get to relativity, we're going to find kinetic energy is different. This 4 times 10 to the 5th velocity is not big enough to worry about relativity. So we're fine. Yeah. All right, so let's write down the conservation of kinetic energy. Now, kinetic energy is a scalar, so that's another thing that makes it nice. I'm going to write down 1/2 mva squared is equal to 1/2 mva prime squared plus 1/2 mvb prime squared, like that. Now, obviously, I can divide through by m's to get rid of them, and then divide through by 1/2 and get rid of them. And I'm ultimately left with VA squared is equal to VA prime squared plus VB prime squared. Oops, I don't like that way that's written. It looks like a 12. So I'm going to say VB prime squared like that. And let's make that one a little cleaner too, just so no one gets confused later. Okay. So that's going to be equation 3. Now, here's where stuff gets dicey. So we've got a system of 3 equations and 3 unknowns. That's good. That's how many we need. And in fact, sometimes if you have like 4, that can actually make it where there's no solution. So it's not always a good thing to have more. But it's absolutely impossible to have less. So 3 unknowns, you got to have 3 equations. 4 unknowns, you got to have 4, so on and so forth. So first thing I'm going to do is get all the subscript a's in equation 1 on the same side. So equation 1 is going to be become this. I'm going to actually, I'll go ahead and do that as one step. And I'll say VA minus VA prime cosine theta A prime is equal to VB prime cosine theta B prime. Now that's not good enough for me. Because I know where I'm going with this, I'm going to also go ahead and square both sides. Okay, now this is just something I know from experience is going to help me. So just hold out for a little bit and you'll see why. So this is going to give me VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared cosine squared theta A prime. The other side is easier. That's just going to be VB prime squared cosine squared theta B prime. And I'm going to call this equation 1 prime. Okay. Now, again, this might not be obvious to you that this is helpful, but trust me, it will be. Now I'm going to take equation 2 and I'm going to do sort of the same thing, square it and everything. So when I take equation 2 and pull the VA to the left-hand side and then square it, I'm going to actually get VA prime squared sine squared theta A prime is equal to, actually, I'm not liking how that turned out. Is equal to VB prime squared sine squared theta B prime. And that's going to be what I call equation 2 prime. Okay. Now I'm going to add 1 prime plus 2 prime. When I do that, that's going to give me VA squared minus 2VA VA prime cosine theta A prime. Now notice when I add the VA prime squared cosine squared theta A to the VA prime squared sine squared theta A, that's just going to give me the VA prime squared. So I'll say plus VA prime squared. Same thing's going to happen on this side, so I just get plus VB prime squared. I'm going to call this equation 4. Okay. Now, what I'm going to do next is I'm going to take equation 3 and I'm going to solve it basically for VB prime. So from this part right here, I'm going to get equation 3 prime. And that equation 3 prime is going to be just this equation solved for VB prime squared. So VB prime squared is going to be equal to VA squared minus VA prime squared, like that. Now I'm going to substitute VB prime squared from 3 prime into 4. And what we get with that is VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared is equal to, now here's where I'm replacing the VB prime with VA squared minus VA prime squared. So what you can see is this VA squared is going to cancel out on both sides, because basically if I just subtract VA squared from both sides, that leaves it in disappearance basically. Now if I pull the VA prime squared to the left hand side, it's going to become positive. So basically from that I can get, actually I'll pull the left one to the right hand side, that'll make it negative. So I'm going to say negative 2VA VA prime squared. Actually, that's not supposed to be squared. Sorry about that. Cosine. Whoa, Dilly. Cosine theta A prime, which is the one we know, by the way, is equal to negative 2VA prime squared. So that's what I've got so far. Let me continue with that on the next page by copying and then pasting and then moving it over here a little bit. Okay, so now that I have that, I think you can see that this is going to give me, notice one of the VAs is going to cancel out. So I use blue to show that. So that cancels out with that one right there. And in fact, this minus will cancel out. And in fact, this 2 will cancel out like that. So ultimately, I am left with just VA cosine theta A prime is equal to VA prime. If we recall our triangles, this being 60 degrees, this being 30 degrees, and the 60 being opposite the bigger side, that makes this square root of 3, that makes this 1, that makes this 2. I can see that the cosine of 60 degrees is equal to 1/2. So now I can say that 4.0 times 10 to the 5th meters per second times 1/2 is actually equal to VA prime. So VA prime is in fact equal to 2.0. And actually, I think I've been able to use 3 sig figs. I just left it off there. Times 10 to the 5th meters per second. So I have one answer. Now I also know that where did that guy go? Let me see. Oh, here it is. So I can take this little 3 prime here. I'm going to paste it right here. And from this, I know, for instance, that VB prime. Amber alert. Sorry about that, everybody. VB prime. Oh, I should be writing this in black. VB prime is equal to the square root of VA squared minus VA prime squared. Well, I know that's equal to the square root of, this is a neat little trick I pulled today. If you look at this, we could call that like Q. And then this, which is VA, is like twice Q. So VA squared here is essentially 4Q squared, and VA prime here is just Q squared. So all this is about me not wanting to use my calculator any more than I have to, and avoiding doing tough arithmetic. So I can now take this and say, okay, well, this is actually the square root of 3Q squared, which is actually equal to the square root of 3 times Q. And of course, I know the square root of 3 is about 1.73, and Q is supposed to be 2 times 10 to the 5th. So really all I have to do is multiply 2 times 1.73. That would be what, 3.4, 3.46. So VB is equal to 3.46 times 10 to the 5th meters per second. I now have that. Now I can also use some equation. Now that I have VA and VA prime and VB prime, I can use another equation to figure out what theta B prime is. So let's look back at our past here. It looks like this equation, I'm going to lasso here. I don't know. Are y'all seeing my lassos when I put them up? I'm going to take this equation. Yeah, it does show that. Okay. I'm going to take this equation right here. And I'm going to copy it. And I'm going to paste it right here. Okay. And from that, I'm going to reach the conclusion that sine theta B prime. Where did that 3 come from? Or did I steal part of a B by accident? That's probably what happened. I must have stole part of a B by accident. So let's get rid of that. That's not going to help matters. Okay. And let's get rid of this one too, because that's not going to help matters. Okay. So from this, I can see that sine theta B prime is actually going to be equal to negative VA prime over VB prime times the sine of theta A prime. So I can say sine of theta B prime is equal to negative VA prime, of course, is 2.00 times 10 to the 5th meters per second. And then VB is actually the same thing times the square root of 3. So I can say square root of 3 times 2.00 times 10 to the 5th meters per second. So that tells me that basically it's just 1 over the square root of 3 times the sine of theta. So that actually can help me figure out what this is supposed to be. Now I know that sine theta A is, or theta A, I should say, is actually 60 degrees. So I'm going to go ahead and put that in as 60.0 degrees. And of course, looking back at our triangle, we can see that the sine of 60 degrees is square root of 3 over 2. So I'm going to get negative 1 over the square root of 3 times sine of 60 is the square root of 3 over 2. So I see that sine of theta B prime is equal to negative 1/2. And of course, that means theta B prime is actually equal to negative 30.0 degrees. Again, this is just me trying my best to avoid having to pull out my calculator. You can verify all this junk with your calculator if you want. But again, we got another instance where the two angles actually add up to give you 90 degrees. Any questions on that? Pretty neat, huh? All right, so we got about 25 minutes left, and that leaves me enough time, I think, to solve the other part of the problem or finish the other part of the chapter, which is about center of mass. So if you'll notice in our module for this week, I posted some video links to my YouTube channel where I actually worked some pretty cool problems, one of which is basically like a train car with a cannon mounted to the bottom so that it actually, the cannon can't move separate from the train car. So when a cannon actually fires a cannonball, then basically you initially had a system where the total momentum was 0 because the cannonball, the cannon, and the car were all sitting still. Therefore, the momentum is 0. Then when you fire the cannonball moves off to the right, say, with a mass times velocity. That's its momentum. Therefore, the train car with the cannon attached to it is going to move off to the left, and that momentum is going to be equal to that same m times v, only this time it's basically through a larger mass. So the velocity obviously of the train plus the train car plus the cannon is going to be a lot lower. Now, as it does that, the train is moving to the left with some smaller velocity, and it's going to continue doing that until the actual cannonball hits the right-hand side of the box. Once it hits the right-hand side, because the cannonball had the exact same momentum that the train car had, the train car is going to come to a stop. And if we force it by putting walls and things like that, the cannonball will fall straight down at that edge. I can then shoot another cannon, shoot another cannon, shoot another cannon, keep on doing that until I get, say, 10 cannonballs off to the right-hand side now. And ultimately, it will result in the whole train car moving to the left some distance. You can figure out that distance by using that conservation of momentum, calculating that velocity while the cannonball is in the air, and then figuring out how long it takes for the cannonball to hit the other side. That's how long it gets to travel at that constant velocity, and then add all those up, and that'll give you how far the train car has moved. That's by conservation of momentum. But what you'll see is I also work it by using a center of mass in another problem. So you can actually see that in that case, and in fact, in general, conservation of momentum leads to the exact same conclusions as center of mass not moving when the net force on the object or on the system is 0, then the center of mass of the system won't move. So for instance, in everyday life, that's sort of why if you're, say, standing in a canoe on the water and you try to walk towards the dock, because you are applying a force backwards on the actual canoe, you're giving it a recoil velocity, not unlike the cannonball gave the train car a recoil velocity. So as you walk towards the actual dock, the train or the canoe is actually going to move away from it. So you're sort of defeating yourself. But what's happening there in reality is the center of mass of the U and the canoe system is staying in the exact same place because the net force is 0. All right. Now, the other important thing about the center of mass is, for instance, if I throw a marker or a pen across a classroom or across the road, the end of the pen is not going to obey that nice little parabolic trajectory that we learned about in projectile motion. In fact, the part that is going to be the center of mass of the pen. So the center of mass of the pen is actually going to follow the parabolic path that we predict from projectile motion. And you could use, for instance, rotational equations, which we're going to learn about in chapter 10, to figure out exactly how much the pen rotates from the second it leaves my hand until the second it hits the ground, and all sorts of cool stuff like that. And then you're actually solving a actual sizable body problem. So the way a sizable body problem works, or a rigid body, is basically you pretend like all the little molecules that make the body up are locked into place with respect to all the other molecules in the body, but the center of mass of the system moves, and then those molecules can rotate around the center, or revolve, that is, around the center of mass, and you can solve all that. And if you know enough information ahead of time, then you can actually predict at what angle the pin will be at the instant it hits the ground, and all sorts of cool stuff like that. So in order to do any of that, we need to be able to compute center of mass. And I hinted to you that the center of mass, for instance, for the x center of mass is actually m sub I x sub I summation from I equals 1 to n over the summation over I equals 1 to n of m sub I. In other words, you take each individual mass and you multiply it by its distance from the origin parallel to the x-axis, and you add all those up and then divide it by the total mass. Similarly, y center of mass is equal to the summation from I equals 1 to n of m sub I y sub I. All that is going to be divided by the summation from I equals 1 to n of m sub I. Again, this bottom is just the total mass. So let's work one of those problems. So what I'm going to do is I am going to make up a problem, and this problem is going to be basically sort of like a tray, like a lunch tray or something like that, that's perfectly square. And, lunch trays more or less have the same distribution of mass everywhere. In other words, any 1 cubic centimeter is going to be exactly the same mass of any other cubic centimeter. So what I'm going to do is I'm going to draw a y-axis, and then I'm going to draw an x-axis like this. And I'm now going to draw the tray like this. And we're going to say this tray is in fact 15.0 centimeters by 15.0 centimeters. And I'm going to say its mass is 1.00 kilograms. Now, what I'm also going to do is I am going to put a mass right here, and it's sort of like a blob of putty, say, but the center of mass of the blob of putty is going to in fact be a distance of, it's going to be a distance of, let's say, 3.00 centimeters that way, and 3.00 centimeters that way. Okay. And this mass is in fact going to be 1.50 kilograms. Now over here, I'm going to say this one is a distance of, let's say, 5.00 centimeters. And let's say this one is a distance of 6.00 centimeters. Actually, I could have drawn that 1,000 ways better. But anyways, this distance right here is going to be 6.00 centimeters. And this mass is going to be 3.00 kilograms. And let's say finally that we're going to have a mass, let's say right here, and this is going to be about 7.50 by, does that look like, so yeah, that looks like 7.50. And let's say this one's going to be about 5.50. And this mass is in fact going to be 4.00 kilograms. Okay. So how do we calculate the center of mass? That's really the problem. So X center of mass is going to be, first off, we start with the tray. Well, the tray is the mass is uniformly distributed, so its geometric center should be its center of mass. I'm going to write, in fact, that its mass, since it's 1 kilogram, I'm going to say 1.00. I'll leave off the units. But, of course, the geometric center would be 7.50 centimeters to the right of the origin, just because 7.5 is half of 15. Then I'm going to say, okay, well, I have this 1.5 kilogram mass over here, and its x coordinate is 3.00 centimeters. And then I have this 3.00 kilogram object. Its center of mass, or its location, is, of course, about 5 centimeters to the right. And then finally, I have this 4.00 kilogram object. And it's 5.5 centimeters from the right-hand side. The right-hand side is 15. So if I subtract 5.5 from that, I get 9.5. So this is going to be 9.50. Now, all of that has to be divided by the total mass. The total mass is 1 plus 1.5, that's 2.5, plus 3, that's 5.5, plus 4, that's 9.5. And again, since I didn't write the masses before, I'm not going to write it now. But basically on top, you have kilograms times centimeters. And on the bottom, you just have kilograms. So it's all going to come out to be equal to centimeters. So when I do this, I'm going to say 1 times 7.5 plus 1.5 times 3 plus 3 times 5 plus 4 times 9.5. That gives me 65.0 kilograms times centimeters. And then down in the bottom, I have 9.50 kilograms. Let me know if you find any errors in my arithmetic. So I'm going to divide the 65 by 9.5. And that gives me 6.84. And I'll write one extra sig fig for good measure, centimeters. So that means if I go over 6.84 centimeters, which should be somewhere right around here, the center of mass will be somewhere on that line. And in fact, if you wanted to balance it, you would put your finger right below that particular spot on the bottom edge, and that would actually allow you to balance it if you had any hope whatsoever of doing so. Now the YCM is the same way, except now I still use the same mass, but I got to use the Y dimensions from the origin. So I'm going to do again 1.00 times, this is for the tray. So the tray has the geometric center at 7.5. So I'll write 7.50 plus the next one is 1.50 kilograms. Now that guy is 3 up. So I'm going to call that 3.00 plus the next one is actually 6 down from the top. Well, the top is 15. So if I subtract 6, that gives me 9. So that's 3.00 times 9. And then the last one is 7.5 from the top. And 7.5 from the top means it's 7.5 from the bottom. So I get 4.00 times 7.5 again. All that will be divided by 9.50. So I'll do 1 times 7.5 plus 1.5 times 3 plus 3 times 9 plus 4 times 7.5. That gives me 69 kilograms times centimeters over 9.50 kilograms. Any questions on that? So we've now found the center of mass. This one will be a little bit lower than the center, but not much. So I would say maybe right along here. That should be YCM. So you can see that particular spot would be where you could balance it in principle. You could hold it like a dinner tray, for instance, where this is perfectly level, and put your finger right under that dot and it would stay. So any questions on that?
How would you go about measuring like an object like that at different parts?
What you normally do is, like, if, for instance, if you took, say, a framing square, you can sort of picture a framing square as either two rectangles. A framing square is like this, and then it's got another piece like that. You could treat it as this is one rectangle that goes from end to end, and then a shorter rectangle that goes from the edge of that one down here. And then you take the geometric center of each of those, since they're rectangles and they're made of usually aluminum or something like that. And there's not one part that's really thicker than the other part or anything like that. So you just take the geometric centers of them and weigh, if you could break it in half, you would weigh the mass of the long one and multiply that by the geometric center, and then take the mass of the vertical one and multiply it by the geometric center, and then divide it by the total mass, and that'll get you the center of mass of that sort of thing. But that's pretty much how you do it. Is you have to consider each object as a point object where its mass is acting like it's right there at the center of mass. And you sometimes have to estimate it. Like, for instance, you could take the whole weight of a framing square, and then you could estimate what fraction of that whole weight, since you can only weigh the whole thing, what fraction of that whole weight is the long rectangle, and then what fraction of that whole weight is the short rectangle. And that, by that way, you could actually figure out the mass of the little parts. So that's the way you do it. Ideally, you're going to have a bunch of little BBs. That would be the best case scenario, because BBs obviously have a very small range from the leftmost edge to the rightmost edge. And in fact, the center of mass is going to be just dead center. So you could always just grab that. That's your best case scenario. But now we've got to go and solve this problem for an issue where we don't have a discrete number like we had here. We had, 4 objects here. That's a countable number. So even if you go up to 17 million, in principle, you can just do the calculation this way. You find the center of mass of each one. To calculate the center of mass in the x direction, you take the x component of the center of mass, multiply it by the mass, do it with the next particle, and then divide it by the total mass, and that'll get you the x center of mass. Does that answer your question?
Yeah, but is there like a way that if you knew the entire total weight, like you could find areas of something, like say you had like a hermetic compressor, and like you knew that you could find the area or the weight at different like areas?
Yeah, let's take, for instance, let me just draw this. For instance, if you had an actual framing square, let's say the framing square, and actually I don't want to do it like that. I want to do it with some nice geometry. So what I'm going to do is I'm going to say the framing square has a length like this, which is 1, 2, 3, 4, 5, 6. And it's not really separate like I'm showing here, but I'm going to treat it like it's separate just to help you understand. So if that was actually a framing square, and that was badly done, what you can realize is obviously this bottom horizontal part is 1, 2, 3, 4, 5, 6.
Yeah, I
6,
see how
8.
you like take and break it up and like add it together, because you know what the mass of like steel is and like the length of it, so you can figure all that out. I was just
Right.
wondering if you like if you knew, like you could pinpoint at certain areas of a single object, you could like go, I don't know. Never mind.
Yeah, using the area is right. So if you got, an area of one part, you take that area and divide it by the total area, then that's the fraction of the total mass. So if you just have the total mass, you can multiply that fraction of small area divided by whole area, and that would give you the mass of that little part. So yeah, you could do that bit by bit to figure out exactly what each of those things were. So yeah, in principle, you could do that. You obviously don't want to go cutting things in half and thirds and stuff like that to actually do it. But the good news is you can always do it like that, just reasoning. You don't even have to use the density or look up the density. A lot of times you can just use the fraction that it takes up. So the fraction of the total mass, or the fraction of the total area, or the fraction of the total volume. All of that works out, long as it's one continuous piece of material, whether it be wood or metal, say iron or aluminum or something like that. If it's just the fixed material, then obviously the fractional volume is the fractional mass. So you can actually just use proportions to set up that. Let me show you another one. Now, it turns out that you can actually calculate the center of mass for continuous objects by assuming they're infinitesimally small. And it turns out the x center of mass is actually equal to the integral of x dm, which is just like x times m, times the integral of dm, which is just like the total mass. And the y center of mass is equal to the integral of y dm over the integral of dm. Now, I did share a couple of those on my YouTube channel, but I shared them on your Canvas page so you can see them. But what I'm going to do now is I'm going to imagine a rod. I'll first draw a coordinate system right here. And that's going to be my x-axis. That's going to be my y-axis. And I'm going to imagine a rod that looks simple enough. It has a length L, but here's the hard part. Lambda, which is really normally called dm over dl. You could also call it dm over dx. If this was a uniform rod, that lambda would be a constant. But what I'm going to do is I'm going to say, assume lambda is equal to 3 x over L plus 1, and make sure the units work out, because it turns out that for this to work, you really have to have the units of lambda to be like kilograms per meter, or the dimensions of lambda to be m over L. So we just make that happen, and that's fine. If I want to do that, what I'm going to do is I have to take this integral and find a little differential mass element, which I'm going to say is right here. And I'm going to multiply that differential mass element times the distance it is away from the y-axis, because that's what x means. So this right here, from here to that inside edge, is x. And in fact, this right here is the distance dx. So it turns out that this thing I can call dm is just going to be lambda times dx, which of course is 3x over L plus 1. That's just something I made up to make it look like, notice if x is 0, the mass per unit length here is essentially 1. And here, the mass per unit length is essentially 4 kilograms per meter. And this one's 1 kilogram per meter. So that's just a function I made up for this particular example. So now I can say the integral of x dm, and we're actually running out of time. It's actually right at 7:40 now, or 6:40 now. So you guys are free to go. I'm going to go ahead and finish this problem. If you can stick around, that'd be awesome. If you can't, I understand. It will be on the video, but I need to at least do this one. And I really wanted to do a triangle, but at least you have the example triangle to work with from my YouTube channel. So let me go ahead and finish this. Like I said, you guys are free to go. I'll keep talking like you're here if you're not here or not. So it's okay. So the top half, which is the integral of x dm, is going to be the integral from x equals 0 to L of x times lambda dm. Well, lambda is 3x over L plus 1 and times dx. So now I get the integral from 0 to L of 3x squared over L plus x dx. And that, of course, is going to give me, notice I get the integral of x squared is 1/3 x cubed. So that's going to cancel out that 3. So I'm going to get x cubed over L plus the integral of x is going to be 1/2 x squared, like that. And then I'm going to evaluate it from 0 to L. So finally, I get L cubed over L plus 1/2 L squared. So that's L squared plus 1/2 L squared. That gives me 3/2 L squared. Now I've got to do the integral of dm, which is the same thing, except it doesn't have that extra factor of x. So I'm going to integrate it from x equals 0 to L. That's going to be, of course, no x. It's just going to be 3x over L plus 1, all that times dx. The integral of this would be 3/2 x squared over L plus x from 0 to L. That's going to be 3/2 L plus L. Notice when you evaluate the 0, it comes up to 0. 3/2 L plus 2/2 L is 5/2 L. So now I know the x center of mass of this is 3/2 L squared divided by 5/2 L squared, and or excuse me, L. Okay, so it just happens to work out so neatly that we get 3/5 L for the center of mass. Easy peasy. Okay. All right, so that's another instance of a calculation of center of mass using, of course, calculus. I'm going to go ahead and work another one. Again, anybody have any questions? You guys are free to go. Like I said, I'm just going to continue working out this example like the one I made up in class today. And the next one's going to be a triangular plate, basically. So let's go ahead and work that. Does anyone have any questions on how I did what I did there? Again, do not feel bad about leaving. Your class was over 4 minutes ago, so it's certainly fine. I'm going to go ahead and now do this other problem. So this other problem is going to be, I have an axis, a y-axis that way. I have an x-axis this way. I'm going to draw a triangular plate. That triangular plate is going to be right here to here. This is going to be a distance W. This is going to be a distance H. And I'm going to assume that this is a triangular plate, is a homogeneous lamina. That's the fancy word that you'll learn in your calculus class. Right now, looking at it, I feel like I want to replace this E with an I, but I have no idea. The lamina just means it's two-dimensional. It's basically very, very thin plate, so it's almost like it's just a two-dimensional object. You could just assume it's like, 16th inch of aluminum plate that's been cut into a length H by W and then cut in half. And what we'll assume is since it's two-dimensional, remember before when I first introduced this to you, I said dm in these formulas can be equal to lambda dl, or it could be equal to sigma dA, or it could be equal to rho dV. Well, this one I'm going to say it's two-dimensional, so I'm going to say sigma is actually equal to a constant, and the constant is going to be its whole total weight divided by 1/2 HW, because that's the formula for the area of a triangle. We're not going to have to use that at all, but I just wanted you to know what it is. The XCM is equal to the integral of x dm over the integral of dm, and the y center of mass is the integral of y dm over the integral of dm. Now, the big thing to remember when you're doing these types of integrals is this differential mass element dm cannot change significantly over the or the x, the integrand can't change significantly over the dm, or you have to do some process by which you find like a center of mass or some kind of averaging process for it. So for instance, if I were to consider a really thin rectangle like this to be my differential mass element, you can see the left-hand side of that red rectangle has x equals 0, and the right-hand side has maybe x equals 7/15, right? So that's a bit of a problem. That's a huge x change. So I don't want that. What I am okay with doing, though, is I'm going to say, let's come out here a distance x, and I'm going to put a little rectangle here, and the thickness of that rectangle is just dx, and the height of this rectangle is going to be that diagonal line minus 0. In other words, it's the y coordinate on the diagonal line minus the y coordinate on the x-axis, and the x-axis is 0. So I'm going to treat this guy right here as my differential area element, and the differential area element, well, let me not write it there. I'm going to say the differential area element dA is actually just that of a rectangle. So its height, you can, go back and use y equals mx plus b, and then realize that this point right here is 0h, and this point right here is w0 and all that. But I can just look at this and know that this function is in fact basically y is equal to negative h over wx plus h. So that's the actual height minus 0. I don't have to write that at all. And then I got to multiply that by dx. So if that's dA, then dm is actually equal to that sigma times dA. So now I can write the integral of x dm is equal to the integral of x times, now I'm going to write sigma, now I'm going to write negative h over w x plus h times dx, and I'm going to integrate from x equals 0 to w. The sigma can come out in front because it's a constant, and I'm going to say the integral negative h over w x squared plus h times x dx. And now I can integrate that and say sigma times the integral of x squared becomes h, negative h over w times 3 in the bottom x cubed plus h x squared over 2 evaluated at 0 and w. So I'm going to get sigma times negative h w cubed over 3w plus h w squared over 2. So basically what I have here is negative 1/3 h w squared plus 1/2 h w squared. This is going to become negative 2/6. This is going to become positive 3/6. So I get basically just 3/6 minus 2/6 is 1/6. So that's 1/6 sigma h w squared. Now I can do the integral of dm the same way. I just don't have that extra x. So the sigma is going to come out in front, and I'm going to have the integral negative h over w x plus h, all that times dx from 0 to w. That is going to give me sigma times negative h over 2w x squared plus hx 0 to w, which equals sigma times, now the x squared is going to become w squared, so that's just going to be negative 1/2 h w plus h w. So hw minus 1/2 hw is actually sigma over 2 hw. So the x center of mass is finally 1/6 h w squared over, and times the sigma, over sigma over 2 h w. And you see everything cancels out except for one of the w's in terms of the symbols. The sigmas cancel out, and we ultimately get 2/6, which is 1/3 w. Now that is the rule with triangles. If they're uniform, the mass is uniformly distributed in a triangle, then it'll be 2/3 of the way from the skinny end to the fat end. So this, if you're looking parallel to the x-axis, the skinny end is out here where the w is, and the fat end is back here. So you either go 2/3 of the way to the left from w, or 1/3 of the way to the right from the 0, and you see you indeed get 1/3 w. That also tells you that you should expect YCM to equal h over 3. Okay. Now, that being said, I'm making this an extra credit. You can solve this whole thing that I just did, and then go ahead and complete it for Y center of mass. I will post an extra credit posting about that, but I'm going to post it on this this module for this week, and y'all can turn it in a week from today if you'd like, and that'll be another extra credit assignment. And like I said, you guys are free to go, but I'll wait here till the last person asks the last question. So shoot, anybody have any questions?
I do.
Go for it, and thank you for sticking around. Go for it.
No problem. No problem. Yeah. Oh. So first, what's it called? Those extra credits, they all do a certain point.
So the way extra credits work that I give you, this is not the practice test. The practice test works an entirely different way. But these extra credits are basically every time you do one, you get a grade, and then the number of dropped homeworks drops by, or increases by 1. So according to the syllabus, I'm supposed to drop your single lowest homework grade. Now I've now made, say, 3 extra credit assignments, that means I'm now going to drop your lowest 4. That's what the extra credits do for you. So if you happen to have done, you know, a little bit bad on 1 or 2 homework problems, that can get rid of it by you making a fairly good attempt at doing an extra credit problem.
Okay.
Make sense?
Yeah. I have another question about my grades.
Okay. Do
I
you
don't know
want me
what.
to pause the video? I don't want to give
Yes,
away.
yes,
Right.
yes, please.
All right, let me stop the video then. I'm going to start off with stop sharing because evidently I don't know how to stop the video otherwise.